Welcome, chemistry students. You are welcome to the second semester chemistry course, General and Inorganic Chemistry. Unit 5 of this course is on acids and bases. Chapter 5.1 of this unit is theories of acids and bases. The instructor for this chapter is Dr. P. Sharada, selection grade lecturer in chemistry, St. Joseph's College for Women, Autonomous, Visakhapatnam. Learning outcomes. By the end of this course, the learner should be able to understand and apply Arrhenius, Bronsted-Lowry, Lewis and solvent system theories to comprehend the behavior of acids and bases in chemical reactions, and also summarize the properties of solutions of alkali and alkaline earth metals in liquid ammonia. Contents. The contents of this chapter are applications and limitations of Arrhenius, Bronsted-Lowry, Lewis and solvent system theories, along with alkali and alkaline earth metals in liquid ammonia. Right from our childhood, we have been learning about the properties of acids and bases. We know very well that acids are sour, they turn blue litmus red, they corrode metals, release hydrogen gas or H plus ions in aqueous media, and the pH of an acid is less than 7. When it comes to bases, we also know that bases are bitter, they turn red litmus blue, they are slippery to touch, they release OH minus ion, and strong bases are caustic in nature and the pH of bases is greater than 7. All this we have learnt in our previous classes itself. Now let us move a little deeper and learn about different theories on acids and bases. To begin with, we learn about the Arrhenius theory, which was proposed in the year 1887, and Arrhenius received the Nobel Prize in 1903 for his theory. Simply, Arrhenius theory proposes that H plus ion donors in aqueous media are acids and OH minus ion contributors are bases. So, what are Arrhenius acids? Simply H plus ion donors. What are Arrhenius bases? OH minus ion donors are bases. So, if you look at the reaction of an acid in water, let us consider our acid to be HA. HA acid in water dissociates to form H plus ions and A minus ions. Since this particular substance HA is contributing to the release of H plus ions, Arrhenius said it is an acid. As an example, you can see here HCl releases H plus ions and Cl minus ions in water. Similarly, H2SO4 releases H plus ions and sulfate ions. So, HCl and H2SO4 are considered as acids by Arrhenius. If you look at the base, according to Arrhenius theory, OH minus ion contributors are bases. So, BOH is the base which releases OH minus ions in aqueous medium. If you take NaOH, NaOH in water releases Na plus ions and OH minus ions. Similarly, NH4OH releases NH4 plus ions and OH minus ions, and hence NaOH and NH4OH are considered as bases. But H plus ions exist as hydronium ions or H3O plus ions in aqueous media. What is neutralization according to Arrhenius theory? Neutralization according to Arrhenius theory is the reaction between an acid and a base to form salt and water. So, you can see here HCl is the acid which reacts with the base NaOH to form NaCl and H2O. And you can see here acid plus base is forming salt and water. So, this is a neutralization reaction. How did you get H2O? H2O is formed by the combination of H plus ion released by the acid and OH minus ion released by the base. Based on Arrhenius theory, the catalytic properties of acids can be explained. According to Arrhenius theory, acids contribute H plus ions. We can see in this particular reaction of cyclohexanol leading to the formation of cyclohexene, the H plus ion that is released by sulfuric acid is the catalyst. It protonates the OH and forms OH2 plus, which is released along with a proton from the alpha carbon atom so as to form the cyclohexene. So, catalytic properties of acids can be explained based on Arrhenius theory. Also, we know that strength of an acid or a base is expressed in terms of acid dissociation constant Ka and base dissociation constant Kb. We can see in this particular equation Ha is the acid releasing H plus and A minus. Now, we can see through this equation that Ka is directly proportional to the concentration of H plus ions. Similarly, BOH is releasing B plus and OH minus, and Kb, which is the base dissociation constant, is directly proportional to the concentration of the OH minus ions. So, you can express the strength of an acid as well as a base in terms of Ka and Kb, because you are able to measure the Ka and Kb values based on the concentrations of H plus and OH minus ions respectively. We now move on to the next theory, that is the Bronsted-Lowry theory, and before going to the Bronsted-Lowry theory, let us look into the limitations of the Arrhenius theory. What are the limitations? It is very obvious this theory is applicable only to aqueous solutions. That is to say, the acid and the base should be soluble in water, or they should be able to form aqueous solution. Then only you can apply this theory. This theory is not applicable to non-aqueous systems. And similarly, it could not explain the acidic behavior of aprotic compounds. What are aprotic compounds? Compounds that do not contain a proton. For example, CO2, SO2, SO3, N2O3, all these are acidic oxides. We know these are the acidic oxides. But you can see obviously here none of them is having a proton. Similarly, it could not explain the basic nature of NH3 and N2H4, that is hydrazine, because both these compounds do not contain an OH in their molecular structure, or in their molecular composition they do not have an OH, but still we know that they are the bases. Similarly, this theory could not explain the acidity of aluminum chloride and other such compounds. So, in order to address these limitations, the next theory has been proposed, which is the Bronsted-Lowry theory. What is Bronsted-Lowry theory? Bronsted and Lowry proposed this theory independently in the year 1923. Their theory is based on protons only. they did not mention anything about OH minus ions. The entire Bronsted-Lowry theory is focused on proton donation and proton acceptance. According to the Bronsted-Lowry theory, proton donors or proton losers are acids and proton gainers are bases. For example, if you take acetic acid in aqueous medium, it releases CH3COO minus, which is the acetate anion, along with H plus. The H plus protonates the water to form H3O plus. Similarly, CO2. Earlier we thought that Arrhenius theory could not explain the acidic behavior of carbon dioxide. Now you can explain it very easily. Carbon dioxide now combines with water to form H3O plus along with the formation of the bicarbonate anion. See, HCO3 minus is formed along with the formation of H3O plus. Similarly, NH4 plus forms H3O plus along with ammonia. HSO4 minus bisulfate ion also forms H3O plus along with SO4 2 minus. So, the acidic nature of all these ions and compounds is expressed or explained based on their ability to generate the hydronium ion. Hydronium ion is formed by the protonation of the water molecule and the proton is released by the particular compound upon reaction with H2O. Like you can see here, HCl plus H2O gives H3O plus, which is the hydronium ion along with the formation of chloride. So, HCl is acid and H2O is base here. What is the definition? Proton donors are acids, proton acceptors are bases. So, HCl is donating the proton to water. So, HCl is acid, water or H2O is the base in this particular reaction. But if you look at the other reaction with ammonia, here you can see ammonia is forming NH4 plus. That is to say, water is releasing the proton and ammonia is accepting the proton. So, that is to say, water is the acid and ammonia is the base. Now, H2O is the acid and ammonia is the base. For example, you can see here HCl is the acid, H2O is the base. Here it is H2O is the acid and NH3 is the base. So, water in the presence of a strong acid will act as a base, and in the presence of a strong base, H2O will also act as the acid. So, H2O can behave both as an acid and a base. You can see here H2O is losing a proton to form OH minus, and in this example H2O is gaining a proton to form H3O plus. So, H2O exhibits the dual behavior of an acid as well as a base. Bronsted-Lowry theory also introduced the terms conjugate acid and conjugate base. What is a conjugate base? The source of a conjugate base is an acid. Acid, after losing the proton, will form the conjugate base. What is conjugate acid? Conjugate acid is obtained by the protonation of a base. A base, after accepting the proton, will form the conjugate acid. Like you can see here, H2O is acting as a base. It is accepting a proton. So, H3O plus is the conjugate acid of H2O. Similarly, the OH minus is the conjugate base of the acid H2O, because OH minus is formed by the loss of a proton by the H2O molecule. You can see here in this example, acetic acid is the acid and H2O is acting as a base now. Acetic acid will contribute or release a proton which is accepted by the H2O molecule so as to form the H3O plus. So, H3O plus is the conjugate acid of the base H2O. Similarly, acetate ion is the conjugate base of the acid acetic acid. You can see here 1 and 2 subscripts are given. 1 will pertain to acetic acid, or you can say the acid. 2 is given to the base. 1 is given to the acid, 2 is given to the base. You can see here acetic acid is forming acid 1 is forming base 1. Base 2 is forming acid 2. So, you get the conjugate acid from the base. You get the conjugate base from the acid. So, the concept of conjugate acid and base has also been introduced by Bronsted-Lowry theory, and another interesting point here is that in higher classes later you will learn that conjugate base of a weak acid is strong and the conjugate acid of a weak base is also strong. See, if the base is weak, its conjugate acid is strong. If the base is strong, its conjugate acid is weak. So, the conjugate acid of a strong base is weak. The conjugate acid of a weak base is strong. Now, let us look at the merits and limitations of Bronsted-Lowry theory. What are the merits? This theory could explain the acid-base behavior of water as well as other protic solvents, like why the same compound can behave both as an acid as well as a base, but there is a small hitch, only of other protic solvents, that is those solvents like ammonia which also contain a proton. And this particular theory is applicable to gas phase reactions also. But this theory could not explain the behavior of non-protonic compounds or the behavior of compounds in aprotic solvents. That is, if the particular compound or the solvent does not have a proton, its acid-base behavior could not be explained by the Bronsted-Lowry theory. You can see here acid is HCl, base is ammonia. So, you have NH4 plus forming as the conjugate acid of the base ammonia and Cl minus forming as the conjugate base of the acid HCl. You can see here SO2 plus SO2 is forming, you can see SO2 plus and SO4 2 minus, BRF3 and BRF3 forming BRF4 plus and BRF2 minus. These reactions could not be explained by the Bronsted-Lowry theory. It could very well explain the HCl and NH3 because they have a proton, there is proton transfer, but it could not explain these reactions which are also acid-base reactions. So, there are some merits, it is an improvement over the Arrhenius theory, but nevertheless this led to the proposition of the next theory, which is the Lewis acid-base theory. Now, let us move to the next theory that was proposed by Lewis in the year 1923, and Lewis theory is focused on electron pairs only. It speaks nothing about the proton or the OH minus ion. Simply electron pair donors are Lewis bases and electron pair acceptors are Lewis acids. Electron pair donors are also called nucleophiles and electron pair acceptors are called electrophiles. Philism is affinity. Electrophile means it has affinity for electrons, so only it is called electrophile, and electrophiles are Lewis acids. Nucleophiles are Lewis bases. Neutralization is simply the formation of a coordinate covalent bond. We know very well that a coordinate covalent bond is a covalent bond formed by the sharing of an electron pair which is contributed by one single atom only. So, formation of a coordinate covalent bond is a neutralization reaction according to the Lewis acid base theory. You can see here NH3 and BF3. NH3 is the Lewis base because it is donating the lone pair of electrons that is present on nitrogen, and BF3 is the Lewis acid because it is accepting the pair of electrons donated by the nitrogen atom. Here you can see boron belongs to the 13th group. 13th group elements are electron deficient. They do not have, even after compound formation also, they do not have an octet of electrons in the valence shell of the central atom, which is boron. Since boron is not having an octet of electrons, it is also having a vacant orbital. Into that vacant orbital, the lone pair on nitrogen is donated. So, you get the NH3BF3 compound through the formation of a coordinate covalent bond. Here the coordinate covalent bond is formed between oxygen and the proton. The hydrogen plus, it is not hydrogen, it is H plus. So, the s orbital is vacant. Into that vacant s orbital on the proton, the lone pair on oxygen is donated and you get the water molecule as the product. So, neutralization reaction is the formation of a coordinate covalent bond between the Lewis base and the Lewis acid according to the Lewis acid base theory. Now, what are Lewis acids? What kind of compounds can be Lewis acids? So, compounds containing central atom with incomplete octet. That means even after compound formation, the central atom, here boron, here aluminum, both do not have an octet of electrons. So, such compounds are Lewis acids. Some cations which do not have an octet of electrons or which do not have inert gas configuration are also Lewis acids. Those that have an octet of electrons or an inert gas configuration, they are not Lewis acids. Ions which do not have inert gas configuration like H plus, Ag plus, Fe3 plus, Cu2 plus, they are all Lewis acids. You can see here Ag plus is reacting with ammonia, nitrogen having lone pair. The lone pair is donated into the vacant orbital on silver, and you can see formation of two coordinate covalent bonds simultaneously with the central silver atom. So, the molecule should contain the central atom, the molecule should have a central atom with a vacant orbital or an ion which does not have inert gas configuration, and also molecules with multiple bonds between atoms of dissimilar electronegativity like CO2, SO2, SO3, etc. When one atom is more electronegative than the other, and when such atoms are bound by multiple bonds, such atoms, such molecules are also capable of accepting electron pairs, and elements with a sextet of electrons in the valence shell like oxygen and sulfur, those that contain only 6 electrons in the valence shell, elements in the elemental state or the atomic state, if the particular atom is having only 6 electrons in the valence shell, all these 4 cases, such molecules or such atoms, they behave as Lewis acids. Those with a vacant d orbital like silver tetrahalide, germanium, phosphorus, those that have a vacant d orbital can also behave as Lewis acids. For example, Bronsted-Lowry theory or the particular Arrhenius theory cannot explain the reaction between SiF4 and F minus to F minus minus to form silicon hexafluoride. The same can be explained by the Lewis acid base theory because fluoride is the Lewis base and silicon, which is having a vacant orbital, vacant d orbital, is the Lewis acid. So, electron pair donation occurs from fluoride to the silicon so as to form SiF6. You can see here if carbon dioxide reacting with OH minus to form the carbonic acid, which is also due to the donation of the lone pair of electrons present on oxygen of the particular OH minus into the vacant orbital on the carbon atom. So, Lewis acids are electron pair acceptors. What are Lewis bases? So, Lewis bases are electron pair donors. Very simple. Lewis bases are electron pair donors. See, you can see here ammonia having lone pair. RNH2 lone pair. You can see this is an ether molecule, oxygen having lone pair. Water, oxygen having lone pairs. You can see all these compounds are Lewis bases. Simple anions like cyanide, chloride, hydroxide, F minus, all these are Lewis bases. Multiple bonded compounds that can donate a pair of pi electrons. They are also Lewis bases. See, earlier case we have seen multiple bonded compounds where there is a difference in electronegativity. Such compounds can accept a pair of electrons. Here these compounds can donate a pair of pi electrons like CO, NO, C2H4, C2H2, all these are the Lewis bases. You can see here ethylene having a pair of pi electrons being donated to Ag plus, which is the Lewis acid. You can see here the formation of this compound. So, Lewis bases are electron pair donors. Ethylene is the Lewis base here. Ag plus is the Lewis acid. So, simply formation of the coordinate covalent bond or formation of a bond by the donation of a pair of electrons by a single atom to the vacant orbital on another atom is what forms the neutralization reaction or the formation of a compound between a Lewis acid and a Lewis base. We now move on to the next theory, which is the solvent system theory or the auto ionization theory. This theory simply states that those solvents will form solvent anions and solvent cations. Solvents, if you dissociate a solvent will form cations and anions. So, what are acids? In water, if you have a substance which is releasing solvent cation for water is H plus, which also exists as H3O plus. So, water undergoes auto ionization, means ionization on its own. Water upon auto ionization will form H plus and OH minus or H3O plus and OH minus. So, what are solvent cations? For water, solvent cations are H plus and H3O plus. What are solvent anions for water? OH minus ions and O2 minus also. You can see here 2 H2O molecules. You can see here 2 H2O molecules forming 2 H3O plus ions and the oxide anion O2 minus. So, auto ionization of water will result in the formation of H plus and H3O plus. So, those substances which release H plus and H3O plus ions in water are acids according to this theory. What is the name of this theory? The name of this theory is auto ionization theory. So, auto ionization theory states that any substance which will release solvent cations upon interaction with the solvent is what is called as an acid, and any substance which releases solvent anions upon interaction with the particular solvent is called as a base. For water, if you consider water to be the solvent, a substance when put in water, if it releases H plus ions or H3O plus ions, it is an acid. If it releases OH minus ions or O2 minus, how did you get oxide anion? When two water molecules form 2 H3O plus ions, an oxide anion is released. So, this is the solvent anion. So, substances capable of generating solvent anions are bases. Substances capable of generating solvent cations in the particular solvent are acids. So, you can see here NaOH is producing OH minus. So, it is a base. You can see HCl here producing H plus and H3O plus. So, it is an acid. So, autoionization theory states that any substance when put in a solvent, if it generates solvent cations, it is an acid. If it generates solvent anions, it is a base. You can see the example of, it's also an implication of Arrhenius theory, you can also consider it as an implication of Arrhenius theory. How you can say that? You can see here, as Arrhenius theory said that H plus ion releasers or H plus ion donors are acids. But it could not explain the acidity of SO3 and N2O5 or NO2, but you can explain it here. SO3 plus H2O, H2O is the solvent, no? Because H2O is the solvent, you are getting the solvent cation 2H plus. You can see here H plus is the solvent cation, so only SO3 is an acidic oxide. You can see here N2O5 is also producing H plus ions, so it is an acidic oxide. Directly Arrhenius could not explain the acidic nature of SO3 and N2O5, but if you combine both, you can explain the acidic behavior of SO3 and N2O5. You can also explain the basic nature of CaO. See, calcium oxide doesn't have an OH minus. Arrhenius theory cannot explain the basic behavior of calcium oxide. But if you put calcium oxide in water, calcium oxide will form calcium hydroxide, which will release OH minus ions. So, it is a base. According to solvent ionization theory or autoionization theory, you can say calcium oxide and ammonia are basic in nature. So, it is also the autoionization theory could also explain certain aspects which the Arrhenius theory could not explain. Covalent compounds like ammonia, hydrogen are considered as basic because they release OH minus upon reaction with water, because they are releasing OH minus ions upon interaction or reaction with water, they can be considered as basic based on the autoionization theory or the solvent ion theory. Yeah. You can see, suppose your solvent is liquid ammonia. Supposing ammonia is your solvent. Now, ammonia, what is the cation produced from ammonia? H plus. What is the other cation that can be produced from ammonia? H plus and NH3 forms NH4 plus. So, the two cations are H plus and NH4 plus. So, those substances that when they are kept in ammonia, if they produce either H plus or NH4 plus or both, they are acids. Those that produce NH2 minus or NH, and so you can see here NH2 minus or NH2 minus, NH2 minus, they are all bases. So, according to the autoionization theory, solvent ionization theory, substances when they are kept in ammonia, if they produce H plus or NH4 plus, they are acids. If they produce NH2 minus or NH2 minus, which is the imide ion, imide, NH2 minus is the amide anion, NH2 minus is the imide anion. If they produce the amide or the imide ion or the nitride ion, N3 minus, N3 minus also can be obtained from ammonia. 4 ammonia molecules will form 3 NH4 plus and 1 nitride N3 minus ion. So, amide ion, imide ion or nitride ion, if these ions are generated by the particular substance when it is kept in ammonia, then you can call it as a base. If it produces H plus or NH4 plus, it is an acid. So, according to this theory, substances when kept in a particular solvent, if they produce a solvent cation, then those substances are acidic in the particular solvent. If they produce solvent anions, then they are considered as basic in the particular solvent. So, with this we close the discussion on the 4 theories. What are the 4 theories we have learnt about? Arrhenius theory, Bronsted-Lowry theory, then we have learnt about Lewis theory. Finally, we are closing with the auto-ionization theory of solvents. So, solvents can be protic solvents and aprotic solvents. What are protic solvents? There are 2 types of solvents, protic solvents and aprotic solvents. So, protic solvents exhibit hydrogen bonding, and because when the proton is present, when the hydrogen is bonded to a more electronegative atom, automatically it will exhibit intermolecular hydrogen bonding. They contain labile protons. Labile means easily releasable protons. So, labile protons or acidic hydrogens, they donate protons to the solute. If you put some substance in protic solvents, that substance will be the solute. So, protic solvents donate the proton to the solute. They can involve in intermolecular hydrogen bonding. Some examples of protic solvents are water, ammonia, and hydrogen, hydrofluoric acid, sulfuric acid, acetic acid, hydrogen cyanide. All these are the protic solvents. What are aprotic solvents? They do not contain labile hydrogens. They do not involve in intermolecular hydrogen bonding. Examples are sulfur dioxide, COCl2, BRF3, etc. Now, let us go to the last part of the chapter, which is about alkali and alkaline earth metal solutions in liquid ammonia. Now, let us look at the behavior and properties of alkali and alkaline earth metals in liquid ammonia. We have seen that ammonia is a protic solvent which is capable of releasing a proton. It can also accept a proton, and then it can also form intermolecular hydrogen bonding. It can donate a proton to the solute. Now, let us look at the behavior of solutions in which either an alkali metal or an alkaline earth metal is the solute and liquid ammonia is the solvent. We know that lithium, sodium, potassium, rubidium, cesium and francium are the alkali metals, and they are the solutes in liquid ammonia which acts as the solvent. Metal ions as well as free electrons are solvated by ammonia. We know, hydrated. Likewise, if the solvent molecules surround the particular charged species so as to reduce the total energy of the system, then you call it as the solvation or the hydration. You can see here alkali metal is represented as M. In liquid ammonia, it forms M plus cations. That is because alkali metals can very easily lose their valence electron to form the M plus unipositive cation, because their ionization potential is very low. After losing that single electron, they get the noble gas configuration. They lose their electrons very easily. All this we already know. Now, metal, alkali metal, when it is kept in liquid ammonia, it immediately loses its electron to form the metal cation M plus along with the solvated or the free electron in the cavity of ammonia molecules. Ammonia molecules will form a cavity in which the free electrons exist. So, this is called solvation. Solvent molecules surround the free electrons. Solvent molecules also surround the metal cation. Now, in very low concentrations of alkali metal in liquid ammonia, if you put very little amount of the concentration of alkali metal is very low, they give intense blue solutions. At moderate concentration of alkali metal, you get bronze colored layer above the blue solution. At very high concentration of alkali metal, you totally get bronze colored solutions. So, this is the unique behavior of based on unique behavior of alkali metals in liquid ammonia, which is exhibited based on the concentration of the alkali metal. Very low concentration, solutions are blue, intense blue. Moderate concentration, there is blue solution at the bottom. In the superficial layer, there is bronze colored phase. And high concentration, you get totally bronze colored solution. Suppose you evaporate the solution of alkali metal in liquid ammonia, you get the uncharged alkali metal. Until now, metal is existing as metal cation, free electrons are there in the solution in the solvated form. But if you evaporate all the ammonia, you get the uncharged or unchanged alkali metal. That is a unique behavior of alkali metals in liquid ammonia. What are the properties of alkali metals in liquid ammonia? The density of the solution containing alkali metal in liquid ammonia is same as ammonia. There is no increase in density. Alkali metal in liquid ammonia, density is same as ammonia. They have very good conductivity. There are free electrons, free ions, so very good conductivity, good conductors. They are paramagnetic. Whenever there are unpaired electrons, such substances are characterized by paramagnetic behavior. What is paramagnetic behavior? The property by which a substance is attracted into the external magnetic field. So, they exhibit paramagnetic behavior, which is characteristic or which is indicative of the presence of unpaired electrons. The G factor of such solutions is same as that of a free electron, and they have nil or weak interaction between solvent and electron. The interaction, there is no attraction or very feeble interaction between the solvent and the free electron. Free electrons exist in cavities of ammonia molecules. Alkali earth metals, if you take, now we are discussing about alkali, but if you take alkaline earth metal, they release 2 electrons and they form the M2 plus cations. They also show similar behavior on dissolution. Evaporation of alkaline earth, if you evaporate the solutions of alkaline earth metals in ammonia, you get alkaline earth metal ammoniates. That means just as hydrated forms, you get the ammoniated form of alkali earth metal. If it is alkali metal, no change, you get only the alkali metal. But if you evaporate solutions of alkali earth metals in liquid ammonia, you get the alkaline earth metal in its ammoniated form. So, these are the properties of alkali and the solutions which are formed by alkali and alkaline earth metals in liquid ammonia. So, we have seen their unique behavior forming 3 different colors of alkali metals in liquid ammonia. We have also seen the properties of alkali and alkaline earth metals in liquid ammonia. So, we come to the concluding part, what have we learnt? So, what did we learn? We have learnt that in aqueous medium, H plus ion donors are acids and OH minus ion contributors are bases based on the Arrhenius theory of acids and bases. And neutralization according to Arrhenius theory is formation of salt and water. Acid plus base forming salt and water is neutralization reaction. Then proton donors are acids and proton acceptors are bases according to Bronsted-Lowry theory, and conjugate acid base pairs are formed. Conjugate acid base pairs differ by a proton. You remove a proton from an acid, you get the conjugate base. you add a proton to a base, you get the conjugate acid. So, conjugate acid base pairs differ by a proton according to the Bronsted-Lowry theory. And electron pair donors are bases, electron pair acceptors are acids according to the Lewis acid base theory, and neutralization is the formation of a coordinate covalent bond according to the Lewis acid base theory. And finally, solvent undergo autoionization and release solvent anions and solvent cations. Substances capable of releasing solvent cation in a particular solvent is an acid, and substances capable of releasing solvent anions in a particular solvent are bases. And we have also seen the properties and behavior of alkali and alkaline earth metals in liquid ammonia in this particular chapter. So, we have learnt about Arrhenius theory, Bronsted-Lowry theory, Lewis acid base theory, and solvent autoionization theory, along with the properties and behavior of alkali and alkaline earth metals in liquid ammonia. Thank you. All the images are sourced from open source public domain websites in this particular video. Thank you.